Hi, welcome back. So today we're going to be talking about a little bit of a slightly different topic. We're going to be talking about universality. So previously, what we had done is I'd introduced the circuit model as well as introducing some basic quantum algorithms, in particular quantum teleportation and superdense coding. Now, what I'd like to do is to be able to show you how, in principle, you can build any unitary transformation that you feel like using a appropriate gate set on a quantum computer. Now, the gate set that we're going to be using for this discussion isn't the final gate set that we'll ultimately want to use, because ideally, a quantum computer should have a finite gate set. The reason for this is twofold. First is, it turns out that there's a theorem that shows that continuous gate sets are in general impossible to implement precisely in quantum error correction. And so what that means is that we're always going to be stuck with a finite number of gates that we can in principle execute with high accuracy on a scalable quantum computer. The other reason is that at some level, no matter what, you have to break any continuous gate setup into a discrete set of gates. So then from that, because of the fact that if you didn't, you need an infinite number of bits of input in order to specify the parameters of each operation. That being said, for simplicity, for the purposes of these lectures, we're going to ignore those concerns entirely and give ourselves freedom to have a continuous set of gate operations. So let's take a look at what those gate operations are. So if you recall, the set of gate operations that we're interested in for single qubit operations are the Hadamard Gate, which can be represented as 1 over root 2, 1 over root 2, negative 1 over root 2. And the Hadamard Gate, as we showed last time, basically is the gate that interchanges between Z and X. And similarly, HXH equals Z. Now, another nice feature about this is using the fact that RZ, which is equal to e to the negative RZ of theta, I should say, theta over 2, 0, 0, e to the I, theta over 2, is the matrix that we're implementing. So what this matrix can be written in the form cosine theta over 2 identity minus IZ sine theta over 2. Okay? And now by Hadamard transforming this, we end up getting RZH is equal to cosine theta by 2 identity minus IX sine theta over 2. And by using Taylor's theorem, we can show that this is equal to e to the negative IX theta over 2 equals Rx of theta. So you can see that basically Hadamard not only transforms X into Z and vice versa, but it also ends up transforming our single qubit rotations to be rotations about originally the Z-axis. We can interpret this as being a rotation about the X-axis if you like a physical interpretation for this. So to get an algebraic interpretation for this, we can actually just plug in identity and X and end up getting that Rx of theta is equal to cosine theta over 2 minus I sine theta over 2 and minus I sine theta over 2 over here and cosine theta over 2 there. Now, my claim is that any 2 by 2 unitary U equals A, B, C, D can be written in the form e to the I delta Rz of alpha Rx of beta Rz of gamma. Okay, so cool. That's basically the form that, that I'd like to be able to use for this. And so now I'm going to prove this to you. So by doing matrix multiplication, we end up seeing that this ends up giving us following. Alpha over 2, 0, 0, e to the I alpha over 2. Now this one is a little more interesting. It's cosine beta over 2, negative I sine beta over 2, negative I sine beta over 2, cosine beta over 2, and then the final one is e to the negative I alpha over 2, 0, 0, e to the I alpha over 2. Okay. Now, when we just go through and do ordinary matrix multiplication, we end up finding that this is e to the I delta over here of e to the negative I alpha plus gamma over 2 cosine beta over 2 negative I sine beta over 2 e to the negative I alpha minus gamma over 2 negative I sine beta over 2 e to the I alpha minus gamma, and then e to the I alpha plus gamma over 2 cosine beta over 2 is the final form of the matrix. Now, what we'd like to be able to do is we'd like to be able to say that this matrix, we can choose the parameters of this matrix such that U0 equals psi for all psi. All right? Now, let's let psi equals square root P0 e to the I theta 0, 0 plus square root P1 e to the I theta 1. Okay, fantastic. And so then, just by looking at this, we can end up seeing one thing immediately. We can end up seeing that we need cosine beta over 2 equals square root P naught in magnitude. Effectively, this ends up implying that we can end up picking beta equals twice the arc cosine of the square root of the probability. So this gives us a sufficient value to pick in order to set the probabilities. Now, in order to be able to produce the phases correctly, what we need to do is we need to end up picking alpha plus gamma equals negative 2 theta naught. And similarly, we need alpha minus gamma equals 2 theta 1. So this gives us everything that we need in order to specify the action of the unitary. And we found this just by multiplying this element and this element by the 1, 0 vector, okay? And demanding that the resulting values ended up giving us the state in question, okay? So that's how we go about doing it. Now, what about the other vector? Because this is a two-dimensional space, right? But a two-dimensional space, you'll have to recall, ends up always being spanned by two vectors that are orthogonal. The only other vector that's orthogonal to this is that, or equivalently, up to a global phase, we can envision rotating about this axis, and every other rotation of this vector is equivalently orthogonal. However, all vectors are equivalent up to a global phase in quantum theory, i.e. psi is equivalent to e to the I phi psi. And similarly, u is equivalent to e to the I delta u, which is why we have this first term over here, to make sure that we have enough freedom in order to be able to set algebraically the overall phase to match whatever this thing is over here. And this is just a unfortunate side effect of the notation that we use for quantum. It ends up leading to us having more than one valid representation for the same configuration as well as the same transformations. So that is what we do, and we can go through and we can pick all of these parameters in an appropriate way in order to make that happen. But this second vector, up to a global phase, is constrained just by orthogonality. So by going through and choosing our angles according to the above rules, we actually already have enough in order to guarantee that the unitary transformation will map 0 to psi, and it'll map 1 to psi perpendicular. Again, because of the fact that all unitary transformations preserve inner product, implies that we know that 0, 1 equals 0 must equal psi inner product psi orthogonal. So, therefore, these two vectors specify every transformation that we can potentially do on the quantum system. And so, that's how we know that we can do all single qubit operations in this way. Okay? So, we've proven universality for a 1-qubit quantum computer. Now, in order for us to be able to make some more progress, what we need to be able to do is we need to be able to talk about something a little more general. We need to be able to talk about universality. Great, sorry about that. So anyways, in order for us to really be able to go through and do universality from this, what I need to do is I need to begin with these single qubit rotations and then gradually generalize them to broader and broader concepts. And these concepts, when we combine them together, will allow us to implement any unitary transformation. And so the idea here was that we showed you that for the single qubit case, that we can carry out any transformation on the 0 vector, and then by orthogonality, this implies that we can do all unitary transformations because the other vector has to remain 90 degrees, sorry about that, to the other one during the unitary evolution. So that is what we're going to be doing. And the next step is for us to talk about controlled single qubit rotations. So I realized something unfortunate. When I was writing this up, at least in terms of the simplest approach for doing controlled single qubit rotations, actually I gave you that the problem of identifying this one of the simplest known approaches as a homework problem. So because it's a homework problem, I figured, well, maybe I should show you a slightly different way than the way that's proposed in the homework in order to be able to do controlled single qubit rotation. So controlled single qubit rotation has a circuit that is represented in the form like this. Recall that theta, down at the bottom, is a free parameter. It's any number you feel like. a real number, I should say. And this action over here will end up mapping a state, in general, A0 psi plus B1 psi. This maps to A0 psi plus B1 RZ of theta psi. So, just like a controlled NOT gate or any other controlled gate, it only applies the gate when this control qubit is 1. Okay? So, that's what we'd be like to do. So, I'll show you a technique that requires Ancillar, but will allow you to do this. And so, the idea of this technique is basically, it basically stems from the following observation. Let's say what we want to do is we wanted to be able to do a controlled Z-gate. Okay, so controlled Z-gate, how does this work? Well, how it works is just, if it's 1 up here, or let's say A0 psi plus B1 psi, this maps to A0 psi plus B1 Z psi. Okay? Or, in other words, it'll return a negative sign if and only if psi is 1 and the top qubit is 1. So, that is how the controlled Z operation ends up getting implemented. But there's many ways that we could end up implementing this. Let's say that we didn't have the controlled Z gate. Let's say we only had a swap gate and single qubit as our gate set. Well, we could implement a controlled Z gate by using the fact that Z0 equals 0. All right? So, what we can do is the following. Okay, let's make that a controlled swap gate. So, we can do this. We add in an extra quantum bit in the 0 state. Now, what we do is if the top bit is 1, then we do a swap gate, controlled swap gate. And a controlled swap gate, just to remind you, is drawn like this. And as your last homework showed, this can be decomposed as the following. Which can also be simplified, it turns out, into following. But okay, but I digress. So this is a controlled swap gate. Now, if we have a controlled swap gate, what a swap gate does is swap acting on psi phi equals phi psi. Okay, so it just switches the two. So we do a controlled swap. Then what we do is we apply a Z-gate down here and then controlled swap back. And let's say this is state X and state Y input over here. So what ends up happening? If X equals 1, then Y will end up getting swapped down over here. Z will be applied to it, and then it'll go back. However, if it's 0, then no swap occurs, and 0 will end up flying through this swap gate. And as mentioned, Z acting on 0 equals 0. So in this case, nothing happens. So this gives you a way of taking advantage of the structure that you know of the eigenvectors of a matrix. Now, just to remind you again what an eigenvector is. An eigenvector is a vector that has the property that the multiplication of the matrix here by the vector there ends up giving us a scalar multiple of the vector. So in this case, the eigenvectors of z are actually just 0 and 1, because these map to 0 and minus 1, respectively. Okay? So we can take advantage of the fact that we know what the eigenvectors are in order to really dramatically simplify our reasoning for these sorts of things, and also simplify our control. We're going to do the exact same sort of thing in order to be able to implement the controlled swap operation. Not the controlled swap operation. We are going to implement the controlled RZ operation. So let's take a look at the following circuit. Instead of doing a controlled Z, let's put in the following. RZ of theta over 2 through here. Now I'm going to do a controlled swap of this and a Ancillar Qubit pre-initialized in the 0 state. Okay, so we've swapped that. Now what I do is I'm going to do the inverse unitary transformation of that over here. And now swap again. And my claim is that what this operation will end up doing is it'll map E0 psi, or sorry, it'll map X, Y, 0 to X, Y, 0 if X not equal Y not equal 1. And it'll map to e to the I theta over 2 X, Y, 1 if X equals Y equals 1. All right. And the way that you can see this is as follows. The first thing is, let's imagine that the case where X equals 0. Okay? If X equals 0, then the controlled swaps don't happen. And the circuit is equivalent to X, Y, RZ inverse 0. That is the identity. So in the event that the top qubit is 0, these two gate operations cancel. And so, just as required, the gate will do absolutely nothing when this top quantum bit, it does not take the value 1. Now, let's assume that it does take the value 1. If it takes the value 1, then the residual circuit that we end up getting from that will be of the form Y RZ of theta over 2 swap 0 RZ inverse, whoops, sorry, swap. Okay. But let's track what ends up happening with the bit. So what's happening with a bit, if there's a swap, then this quantum state ends up going down here, and that one will end up going up here. So the state that we end up getting back out is we end up getting RZ theta on 2 acting on the state Y, and we get RZ inverse of theta on 2 acting on the state 0. Wonderful. Now, let's take the case where y equals 0. If we end up getting a case where y equals 0, then just from looking up what RZ is, this ends up yielding e to the I theta over 2 minus 0, e to the I theta over 2, 0, using the fact that RZ inverse equals RZ dagger equals RZ of minus theta over 2. Okay, so because these two are scalars, they're not matrices, they're just numbers, we can move them around any way we want in this vector product. So this is just equal to 0, 0. Now, let's take a look at the case where y equals 1. Then, in that case, something changes. We end up getting just the same. We get e to the I theta over 2, 1, because the sign of this one flips. And then we get e to the I theta over 2, 0 over there. Combining these two, we get e to the I theta, 1, 0, as claimed. So, in the event that both controls are 1, oh, I'm sorry, I was wrong about that factor of 2. So, in the event that both x and y are 1, then this quantum circuit will put back a phase. But this is a little bit different than the controlled RZ circuit. So the controlled RZ circuit, right, it should map 1, 0 over here to 1 RZ theta of 0, which is not equal to just 0. Because the only thing that we ended up doing over here is we ended up switching the phase for the 1 component. So we can do this actually by noting that if we apply a NOT gate, we can map 0 to 1 through a single application of the X. So what that means is that we can combine these two together to first update 1 to e to the I theta 1 over 2. And then we take 0 to e to the minus I theta over 2, 0. Okay, and that's basically the idea. And so this circuit over here ends up taking the form RZ inverse swap. So this does the correct transformation for the state 0, 1. Now what we do is we flip 0 to 1 by putting it through an X gate. Then we do the exact same thing. However, note the phase we need is the opposite phase. So we are just going to end up flipping the direction of each rotation by turning it into its inverse. So we do that. Okay. Then we do an RZ of theta over 2 that, and because of the fact that we always end up reverting our qubits back, we have to apply an X gate at the end to counteract the NOT that we did over here. And that is one way that you can implement a controlled rotation. So see that this circuit ends up requiring 4 single qubit rotations and 4 Toffoli gates, effectively. The reason why I say 4 Toffoli gates is, again, controlled swap can be decomposed into a Toffoli, a Toffoli and 2 controlled knots, like that. All right, great. So that is how we end up doing a controlled rotation. Now, if we want to do a controlled single qubit rotation, single qubit unitary, which is the natural first generalization that we're going to consider for the previous case, what we need to do is we need to replace the standard unitary decomposition, which again is e to the I delta r z of alpha, rx of beta, rz of gamma, with the following circuit. Okay, first we put a control. This is the control line up at the top, and this is the target state that we want to be able to apply it to. Okay, so first thing that we do is we do Rz of delta, then we do Rz of controlled Rz of gamma, where we use the above circuit to implement that. Now we need to do a controlled Rx. We can do a controlled Rx using that trick that I showed you earlier by Hadamard conjugating a rotation. We can convert a Z rotation into an X rotation and do this middle one. Then finally, we do Rz of alpha. Now, the observant amongst you might realize, hey, wait a second. How come the order of these parameters is the opposite of the ordering that you gave above? This is an unfortunate consequence of the conventions that were chosen with matrix multiplication and the quantum circuits. For matrix multiplication, the time ordering ends up going in this direction. So the first operation that you apply to a vector, psi, is this one. And the last one that you apply is that one. Similar, but on a quantum circuit, we define time to go from left to right. And so this operation is the first one, just like we end up seeing over here. So that's the reason why, is that both quantum circuit diagrams and matrix multiplication make opposite conventions about whether right means time or left means time. Okay, great. The next thing I wanted to clear up is this thing. Now, you remember me saying that the global phase for every unitary is irrelevant. So e to the I delta u is equivalent to u. However, for a controlled operation, this isn't the case. So, for example, let's take a look at the let's take a look at a simple example of a controlled gate. So we have two operations. I've got the identity operation and minus the identity operation. Okay? So controlled identity gate is a really stupid gate. It basically does absolutely nothing. However, if we have the controlled negative identity over here, what this will do is this will map 1 and psi to negative 1 psi. So the controlled negative identity is actually equivalent to the circuit Z psi, okay? Which is a somewhat trivial circuit, but the key point that I wanted to bring out is that the global phase of the unitary matters if you're controlling. The reason why is because of the fact that the control ends up kind of setting a global perspective on what the phase is. You've got to set the phase here relative to this global behavior, and you can't just arbitrarily do that if you demand that 0 phase is kicked back when a 0 is put in up here. So that's the reason why we want to apply e to the I delta, but we only want to apply e to the I delta when this is 1. And RZ of delta up to a global phase is, well, okay, I'll write in the global phase explicitly, is e to the minus I theta over 2, 1, 0, 0, delta, e to the I delta. So if we want to get the e to the I delta coming through when the control qubit is 1, RZ of delta will do that, and up to a global phase. If the control qubit is 0, then no phase will be accumulated, and thus the circuit will do absolutely nothing when 0 is put in. Therefore, this circuit implements a controlled single qubit unitary. Because, again, in this particular case, every single qubit unitary can be written as e to the I delta, RZ alpha, RX beta, RZ gamma, as we showed earlier. Great. So now we know how to do all single qubit unitaries and all controlled single qubit unitaries. Now, actually, we just have to do one final step. And the final step is to combine these two ideas together in a way that will actually allow us to manipulate a matrix to end up... Oh, okay, you'll see. So, final step, universality. So the way that we're going to do this is what we want to be able to do is we want to be able to find some sequence of operations, U1 through UK, such that this is equal to U. Okay? So we want to find a sequence of these ideally controlled single qubit rotations to implement this. Now the gates that I'm going to assume that we have here for simplicity, I'm going to assume that we've got Toffoli, and I'm going to assume that we have our Z of theta for all theta in real, and I'm going to assume that we have the Hadamard operation. Okay? So those are the tools that we have at our disposal. So what we'd ideally like to do is we'd ideally like to be able to come up with a good way of solving this equation. Now an easy way of solving this equation is actually just by doing the following. We can say that identity is equal to UK dagger, U1 dagger, U. So if we can find a sequence of matrices such that when we left multiply the target unitary we want to build with them and get the identity, then we can just work backwards and say, okay, well, I know what the first one is because I figured out what UK dagger is. I'll just use the fact that UK is equal to UK dagger dagger. All right, and that will end up allowing us to work backwards and find out the specific sequence of unitary transformations that will end up making this happen. So, in order to understand this, let's look at a more modest task. Let's envision that U is of the form U00, U01, all the way down to U0, D minus 1 over here. And then we have U10, all the way down to UD minus 1, 0. And I'm going to write this in block diagonal form. So I'm going to assume that this is a block matrix. So our goal is to end up finding first a sequence of U1 or UK through U1 such that U acting up here is equal to 1, 0, 0, U01 prime, U0 D minus 1 prime, and for some other block diagonal matrix or block matrix in here, MD minus 1. Okay? So basically what I'm saying is I want to be able to find these unitary transformations that zero these over there. Now, recall that this is a unitary operation. So therefore, U dagger is equal to U inverse. The only way that we can have that is if the first row ends up being also zero, except on the diagonal. All right, so that is how we can end up doing this. So now that we know that the problem of diagonalizing or of finding this sequence is equivalent to finding a sequence of rotations that makes the first column 1 with a whole bunch of zeros following it. Let's reduce that to a simpler task. Let's now take a look at the task of converting a rotation with. Let's look at the task of converting a rotation inside a two-dimensional space into a single qubit rotation. So for example, let's say what we want to do is we want to be able to do the following. If we've got a matrix that is of the form A, B, C, D over here, and 0 everywhere else, you can see that this is equivalent to doing a controlled rotation inside this two-dimensional subspace up here, spanned by that block. So how do we end up doing this? Well, the simplest thing to do is that by permuting the rows and columns, what we can do is we can map this to A0, going all the way across to B, down to C, 0, D, and 1 everywhere else. And basically what I've done over here is I've done the following permutation. I have done 0 goes to 0, and 1 goes to D minus 1. Okay? So this permutation will end up turning it into that particular form. And if D is a power of 2, then this will give you a way of expressing this as a single qubit rotation, or a single qubit unitary. But I'd like to be able to do this a little bit more broadly. in order to be able to, I like to be able to use extra Ancillar Qubit to show you a particular construction for doing this. Now, if you want to see an alternate treatment of this, you can look up Nielsen and Schwang, and in there, they give a construction based on gray codes that will work and will require less memory. However, I like this approach a little bit better because I think it's clearer than the gray code example. And also the other reason is because of the fact that these ideas generalize much nicer to ideas from quantum simulation. So here's the idea. What we want to do is, this idea begins with the following observation. What we have is we have a situation where we want to apply an arbitrary 2x2 unitary to only this block. However, this block is, again, 2x2. A qubit is also 2x2. So what we want to do is we want to map the relevant 2x2 subspace to a qubit. Then do controlled unitary to perform ABCD on it, then map back. So that is our strategy for implementing this over here. We convert this problem, which we don't know how to solve directly, to the problem of carrying out a controlled single qubit rotation on a qubit. This approach over here, it works nice, it's relatively efficient. However, the downside is you need one extra. Actually, the way we're doing it, we're going to use 2 extra qubits in order to be able to carry this out. Okay? So that's the idea. So imagine now that we have a generic block for this. We've got A, B, C, D. And let's assume that this occurs in row X, and this occurs in column Y, or row Y. Similarly, this has to occur in column X and row Y, where X is strictly less than Y. Okay, great. So if that's the case, now let's begin with a arbitrary input over here. Okay, so let's let psi equals then AX plus BY plus C perp, where this is orthogonal to X and Y. Okay, great. So now what we're going to do is we're going to do the following set of transformations. First thing we're going to do is we're going to end up applying a bunch of NOT gates to map this to AX exclusive OR not X. Sorry. A exclusive OR X, all not. Plus B, Y, exclusive OR X, all knotted. Plus whatever these perpendicular vectors are, exclusive OR X, all knotted. All right. Now, in this particular case, what we end up getting is we'll end up getting X XOR X, this will be 0, 0, 0, 0, so on and so forth, 0. But we're knotting it, so we'll have 1 all the way down in 1. Now, for this over here, we have no idea. I don't have any idea what this could be. It will just be that, and similarly, I don't know what this is. So I'll just leave it as is for the moment. Okay, great. Now, let's introduce 2 Ancillar qubits. These qubits are going to be used for 2 purposes. Okay, this first one we're going to use as a control. And the second one we're going to use as the qubit target. So now, by doing a bunch of an n-controlled Toffoli, it's basically going to be computing the AND of all of these. And this will end up yielding a 1 all the way down to 1 over here. 1, 0. Now this cannot be 1, 1 because of the fact that we've assumed that x is less than y. Ergo, this can't be 0. Ergo, this can't be all 1s. And the n-controlled Toffoli gate will only output 1 if and only if this whole vector is 1. So therefore, this will end up yielding b y exclusive or x not 0, 0 plus so on and so forth. All right, sorry about that. Now, that is the first part of the construction. Second part of the construction, what we need to do is we need to now apply, again, a bunch of NOT gates in order to undo this and map that to a x, now exclusive or y, not over here, plus b, now this one's all 1s, plus exclusive or x bar over here. Oh, and I should mention that this is 1, 0 there, and this is 0, 0, and this is 0, 0. Now I'm going to do the same thing in controlled Toffoli. And 1, well, I guess we can do this as 2n controlled Toffoli gates in order to map this to a x XOR y 1, 0 plus b 1 all the way down to 1. This will be 1, 1 now, plus c exclusive or x not 0, 0. Okay, that is our transformation. Now, let's rewrite that. Let's undo all of those knots. By applying a bunch of knot operations, we'll undo these calculations in order to get ax 1, 0 plus b y 1, 1 plus c 0, 0. Okay, now I'm going to rewrite this in the following way. I'm going to rewrite this as ax plus b y one 0, 1. Okay, so now that I've written it this way, I want to show one thing. What I can do is, from this particular value, I know that 0 has to be paired with x, and 1 has to be paired with y here. So if controlled on this bit, what I can do is I can then do a sequence of Toffoli gates to end up mapping this to 0, 0, plus B 0, 1, 1. And now I can write that as 0 out here, A 0 plus B 1, 1. So all of the information that we need in order to be able to evolve the quantum state is no longer stored in this isolated two-dimensional vector space like it is up here in this block over there. Now we've transferred all of this information to a single quantum bit. So if we want to take psi equals A0 plus B1, oh, and I forgot that we also have this state that's orthogonal over here. Now, if we want to do that, then all we have to do is do a controlled operation on this flag over here, which tells us whether we're in the subspace spanned by x and y, or whether we're in its orthogonal complement. So what this means is that we can do a controlled unitary operation to map that to 0, U A 0 plus B 1, 1 plus C orthogonal 0, 0. So this gives us a way of manipulating each of these individual states and applying a transformation on it. Then undo calculation for everything but the controlled unitary. So that switches the basis back. That ends up causing us to go from, this representation where we had our information, say, in a block, right? Down here, you have a larger matrix, to a transformation that ends up going like identity, tensor, a controlled A, B, C, D. Okay, so that is basically how this whole construction ends up working, and gives us a way that we can implement a unitary transformation on any two-dimensional subspace. Okay, now this ability to be able to perform a transformation on an arbitrary two-dimensional subspace, we can use this in order to solve the zeroing problem. And by that, what I mean is, what we want to be able to do is we want to be able to, in general, find some matrix U tilde for a two-dimensional subspace. Or, let me try this again. What we would like to be able to do is we would like to be able to come up with a unitary that maps U0, 1 going all the way down to UD minus 1, U1, 0 all the way down to UD minus 1, 0, and some other block over here. Let's call it MD minus 1 in here. What we'd like to be able to do is we'd like to be able to zero out these elements. Now, our algorithm is recursive. First, what we want to do is draw this explicitly in here. We'll want to take a look at this top block. Now, we're going to want to apply a unitary that will make this element 0. Then, what we'll do is we'll go on to the next one. Make it 0. And modify the rest of these. So on and so forth. And make all of these guys 0, one at a time. Because each of them is equivalent to performing a rotation on a two-dimensional subspace, this process actually involves us just applying this controlled two-level unitary over and over and over again. So to see how this works, we know that we can apply a unitary to any two-dimensional space. We just need to figure out what that two-dimensional unitary should be. So we need to figure out a unitary such that U tilde acting on A, B, C, D is equal to A prime, B prime, 0, D prime. Okay? And actually, there's we can figure this out pretty easily. So let's let U tilde equal W, X, Y, and Z. Now, if that's the case, then we end up getting WA plus ZC has to equal 0 if X, Y, W, Z, A, B, C, D equals A prime, B prime, 0, D prime. Now, I'll emphasize what I mean over here. I haven't specified these components because we really actually don't care. All that we need to do is we need to diagonalize a first column, because from unitarity, that will guarantee that once we've removed all of these non-zero elements, we'll actually remove all the non-zero elements from that row. So, okay, fantastic. So now what we end up getting is we end up getting that, that this condition over here ends up yielding W equals ZC over A. And a appropriate choice of U tilde then ends up being A over square root of A squared plus C squared. C complex conjugate over A squared plus C squared. C over square root A squared plus C squared minus A over square root A squared plus C squared. This implies that, provided that A is not equal 0, this ends up giving you a good way of figuring out how exactly to end up choosing your unitary in order to deal with it. In the event that A equals 0, there's an easy trick that you can do otherwise. So, we go through line by line, handling these as using these transformations. So we need to apply this approach once, twice, all the way down to D minus 1 times. So this process has to be done D minus 1 times in order to map this to 1, 0, 0, all the way down, M prime D minus 1. Okay? So what we've done is we've effectively zeroed out everything except for this block over there. Now, what we need to do is we need to just argue how many times we're going to need to do this. So we'll need to do this sum from D equals 2, or actually let's say 3, going down to D max of D minus 1. And this is in order D squared. So basically, the number of fundamental operations that we end up needing in order to be able to implement an arbitrary unitary matrix scales as D squared. Okay? So that's actually, that seems pretty good. In fact, you can see from a counting argument that D squared should be optimal. The reason why is that we have, everything considered, D squared different numbers inside here. And so in the event that it required less than D squared operations in order to do that, then what we'd be able to do is we'd be able to choose one of these cells over here and get it to idiosyncratically change its value compared to the rest of them. And then it would be impossible for us to figure out what exactly that value was. And so because of the fact that in principle we could choose all of these values completely arbitrarily, we're going to need d-squared gates in order to be able to specify them, just to ensure that the amount of information in the representation is equal to the amount of information stored in the matrix. So that is basically how this universality construction ends up going. The final thing that I want to mention is, again, what is D? D over here is the dimension of the matrix, which is 2 to the number of qubits. So this exact synthesis method, it could realistically be done for n qubits less than or equal to about 20. Beyond that, it becomes incredibly challenging to be able to do it, because in effect the number of operations that we would need to do would ends up going like 4 to the 20, and that is a very big number. So this means that, well, this approach ends up showing that we can in principle build any unitary we want using this construction by using these two-level unitary operations. This ability doesn't actually give us the power to be able to do exponentially large quantum operations, which is what we're going to need to do to get a quantum advantage. So, really, well, this approach proves universality. Where specialized techniques will be needed to implement specific quantum algorithms. Okay, and in particular, we're going to have to come up with more cunning ways, or choosing more structured problems, in order to make sure that we can actually build these exponentially large quantum operations using fewer gate operations than 2 to the n. So that's basically that. And as we begin to go forward, looking at other quantum algorithms, you'll start seeing some of the key techniques that we end up using for doing this. All right, well, thank you very much. Hope you guys managed to follow most of that, and yeah, I'll see you around next time.